And hopefully you should be able to see my screen now. So on the right-hand side, I'm going to be showing a script in my text editor. It's just Sublime Text over here. And on the left-hand side of my screen, I'm going to be showing the Python interpreters. So let's go ahead and open that. And so just to jump in as a full disclaimer, all of this is very beta. We're beta testing. Please submit bug reports if something doesn't work. And the load times for some of the MMS data are slow, and this should be fixed soon. In fact, if you loaded data last week, and you might want to update to the latest version today, because we've had some updates in the past couple of days that have significantly increased or decreased the load routine times. So for the agenda, I'm going to just introduce everything and then go into loading MMS data in Python. Then we're going to talk about plotting MMS data in Python. I'm going to show off a couple of analysis tools in pySPEDAS, and then we're going to talk about future plans. So for the introduction, all this development is occurring on GitHub. So it's just to find the repo, just go to github.com/speedas, and you can just click pySPEDAS. And so all the developments there. So to download to actually get started, you can either use pip or pip install pySPEDAS, or if you want the latest updates, download the bleeding edge from GitHub, and that's just this download button over here, download zip. The one thing to note is that if you use the download bleeding edge from GitHub, you'll have to install the requirements using pip install requirements or pip install -r requirements. So I definitely suggest trying pip install PDAS first, because that'll actually install all the requirements automatically. Also for configuration, all the configuration settings for MMS are in a file called MMS_config, and that's in the MMS folder. So to find it, you just go into pySPEDAS and then MMS, and then it's MMS_config. And the hash table here stores your local data directory. I put a debug mode in for myself. It just makes it much more verbose and tells you more about what's happening behind the scenes. Download only will avoid loading the variables into tplot. So that'll just download the data only, the data files. And no download will only load the data files if they're found locally. It'll avoid going out to the science data center to grab the files. And we also support the root data dir directory or environmental variable. And we also support the MMS data dir environmental variable. So if you have those set to load the data in IDL, it should automatically just grab those and know your pack or know where your data is stored automatically. And another thing I should note is that all of this is enabled by a project called pytplot that's being developed at last by Brian Harder. And and that's just github.com/mavensdc pytplot. But to get there, I usually just Google pytplot, and it takes me directly to to this page. And if you need to find info on the MMS data sets, go to the last SDC /datasets. That's it's really advised before doing any science that you actually go and find information on the data sets and contact the instrument team and let them know what you're up to. And one final thing, when you're so we're going to be importing a lot of load routines as well as tools to actually work with the data. And all of this is actually stored in a file called Python startup. So you can set the Python startup environment variable to this file, and it'll allow you to avoid having to manually do all these imports of the load routines as well as the basic tools. I have an example of that here. You see it loads all of the MMS load routines as well as the pytplot functions for operating on the data, and some pySPEDAS tools for doing time conversions. And so the idea behind this is that when Python, if you set the Python startup file to this file, it'll automatically call all of this when you open Python, so you won't have to actually do it in a script like I'm going to show here. So for loading MMS data in Python, the load routines follow the same format as in IDL. It's MMS_load_, and then the instrument. So and we support MEC, FGM, SCM, EDP, EDI, EAS, FEEPS, HPCA, FPI, and ASPOT. So it should be all of them. And there's also DSP. Yeah, put that one in there. It's the digital signal processor. So let's go ahead and load some Python data, or load some data. So to get started in the Python interpreter, you just import your load routine from pySPEDAS.mms. So, and the first time is going to take a little more time because it has to actually set up a lot of stuff. And another thing to note is that all the defaults for the load routines should be pretty much the same, with the one exception being the T range, the time range. In IDL Python or in IDL SPEDAS, if you don't specify a time range, it'll prompt you for a time range. In Python SPEDAS, it just uses for MMS, it just uses our default date of October 16, 2015. It's kind of our favorite date to load data for. So they're load MEC files, you just call MMS load MEC. And if you don't specify a probe here, it loads probe 1. But in this case, I specified probe 4, so it went out and grabbed probe 4. And in this case, I already had probe 4 loaded or saved locally, so it went out and found it and loaded the variables. And notice that it actually printed out all the variables that it loaded. It also returns the variables that it loaded. So you could say loaded MEC bars equals, and it should, well, load the file, and it will actually return the variables in that loaded MEC bars variable. And if you want to find help on a MMS load routine, you just call help, the help function on the load routine, and it should print out the documentation. So in this case, I just showed the MEC example. This function loads MEC data into tplot variables and has all of the keywords. And just like MEC, you can load data from the other instruments. So you can import FGM and go ahead and load some FGM data. So in this case, we're loading probe 4, burst mode, just 1 minute of data, and we're time clipping it. So just like an IDL, we don't time clip to the exact T range by default. We find all the data we can within that time range, and any data that's within those CDF files also gets dumped in there. And we don't do the time clipping automatically because it takes time to actually do that time clipping. So we have a keyword just like an IDL to turn time clipping on if you want to clip the requested time range just to your requested time range. And notice that it actually told us that it was doing the time clipping as it loaded the data. And so if you want to find out what variable names have been loaded, you just use the function tplot_names, just like in an IDL. So import it and then call it. And just like an IDL, it gives you the tplot number and the tplot variable name. And we can load some EDP data. This is the electric field instrument. And for that same interval, just have to call the load routine. I think this one takes a little bit longer. But also another way of accessing the loaded tplot variable names is a function called tnames, just like an IDL. And this accepts an argument that you could either do just empty nothing, or that'll return all the tplot variable names, or you can give it a string and say load all EDP bars. And this will return all the EDP bars. So this EDP variable should be done pretty soon. Let's see. Also DC. So this is one of those cases where the load routines should be a lot faster than it currently is. We could always open another Python terminal. So in addition to the datetime strings, the T range can also be specified as datetime objects. So, for example, we can import our MMS load FGM and then import the datetime object and the time zone object. And the thing to worry about here about the datetime objects is the time zone. If you don't specify a time zone in here, it'll use your local time zone, and then we convert to UTC internally. So you might have a difference between your time zone and UTC. So you should all, if you use datetime objects, be sure to specify the time zones in UTC. So it looks like we have our EDP variables loaded, so we can. Oh, so we have to import T names before we use it. And that should have returned the DCE bars. Yep. And you notice I call tplot names or T names without any arguments. It'll list all of the variables that are loaded. So let's go ahead and load some FPI data. This time we're going to use datetime objects, with start time and an end time. This is useful if you have other Python code that already has the time range or time set as datetime objects. You can just pass them to the T range keyword. You can see it did the conversion internally and found out the right times.
So is FPI centered in here? Like in ideal, we have center measurements. FPI is centered.
So not yet, but soon.
Okay.
I can add it soon. Yeah, I'll have to add. Actually, let's go ahead and add that to the bottom of the list. That's a great suggestion. So, so now if you want to get the actual data out of a tplot variable, so you just use the get_data function from pytplot. So just import that and then call times, so get data returns a tuple with times and then the FGM data stored as a NumPy array. So your times should be actual times in Unix time, and the FGM data should be, notice that this is actually a vector plus the magnitude. So they store the magnitude as well as the vector in these. So if you want to print out the Unix time, the first Unix time in the data set, that's it. If you want to print the first vector plus magnitude in the data set, you can just copy it over there. If you want to convert the Unix time to a time string, just import time_string from pySPEDAS and then call it on the Unix time. Notice that converted it to the correct time. And of course we have time_double also in pySPEDAS, so you can convert that time string right back to the same original Unix time. And it's good that it's self-consistent. And of course, along with get data, there's also store data for actually creating tplot variables. So just go ahead and import store data, and we can, in this case, we can, instead of storing the data as a vector plus the magnitude, we can store two tplot variables, one with the vector and then one with the magnitude. One thing to note here is that in this, when you're slicing Python data, the first index is inclusive, but the second isn't. So this means save 0, 1, and 2, but not 3. So that should create a tplot variable called b_vector with just the first 3 elements. And then here is b_mag, which should create a tplot vector or a tplot variable called bmag with just that magnitude, which is the last element there. And I wanted to show some more examples of load routines, and including how flexible load routines are. So you can specify as a string, you can specify probe as a string, an integer, an array of or a list of strings and a list of integers. Data type also accepts the list as well as a string. So is data rate. So we can go ahead and load a whole bunch of HPCA data. So I specified this is probes 1, 2, and 4, and both data types, ion and moments. And that was pretty fast. Also load some EIS data. And in this example, it's just we're loading both the energy by time of flight and the pulse height by time of flight data. And by default, it just loads the energy by time of flight data. And I also have an example here with feet. And we also, so all of these load routines have the keyword get support data to load.
Question, sorry.
Yeah.
So when you say the data type moments and ion, that means the ion moments and the ion distribution function?
Yes.
Is that, okay.
Yep. And so, yeah.
Great. I wanted to know, thanks.
Okay. So the get support data gets all the variables. It also loads all the variables in the CDF files that are labeled support data. By default, the load routines only load the science data. With the one exception being FGM right now. The FGM data turns on get support data by default because we removed the flagged data that are the data that are flagged by the team by default. And there's a keyword for turning those flags back on and getting the original data. I think it's keep flagged. It all works. The idea here is for it to work exactly like it does in IDL. So I guess now we learned how to actually load a bunch of data, and we should probably get into plotting it. So here's how you plot data. Just import tplot from the pytplot package. And this is pretty great because you just call tplot on the variable name and creates a window. And this is interactive, so you can see the time and the data and the measurements. And let's see, instead of just doing a string, you can do a list of strings. So it's plot two different tplot variables. This is the FGM data and the electric field data. And if you want to modify some of these plots, you just change the plot metadata. And just like in IDL, it's you import the options from pytplot. Once you have that, you just call options on the variable names. In this example, I'm going to change. Notice that by default, when we load FGM data, we're setting the plot metadata. So we're getting the labels and we're getting the y-axis title correct. But when we load the electric field data, we're not doing any of that yet. That'll be fixed soon, but I also just wanted to use this as an example to show how to set that metadata manually. So you just call options on the variable you want to change and set the option, and then the options, the actual attribute. There we go. And we're also going to set legend names, which is the labels. And then you can go ahead and create a tplot window. This time I'm including both those two, the FGM data, the electric field data with the updated metadata, and energy spectra from FPI that we loaded earlier, and the pitch angle distribution, the middle energy pitch angle distribution. So you notice that the electric field data now have the updated colors and the labels, but I didn't update the y-axis title yet. But y title is the option for that. So if you want to find which options are available, go to pytplot. And this is how I do it anyways. I think you can also do help. I pretty much always just go here and look in the files themselves. But these are the options. And if you look in the files themselves, you can actually see some examples and how it works internally. That's mostly why I go to the files themselves. And another example would be the B vector that we created earlier. If you plot that, it's not going to have the metadata that the FGM variable had because we created this tplot variable from scratch and haven't set any of the metadata yet. So we can go ahead and set the Y title. Set that to, notice that now it's just the variable name. We can set the colors just like before, and then legend names, just like we did for the electric field variable. Create another plot. This time it has the metadata updated. That was easy. And so what about if you want to add vertical bars at certain times to label a time? There's just like an IDL, there's time bar. So you just import time bar from pytplot and then call it on your variable name, which this time we're going to give it the FGM and give it the start time and the end time. And this also, just like an IDL, it should support the data bar keyword, which allows you to add a horizontal line instead of a vertical line. I haven't done that in this example, but I saw that it should allow it. So once you add the time bar to the variable, you just call tplot on the variable, and notice that you've got 2 vertical bars at the times that's specified here. So it's 620 and 640. And another example, we can plot some number density from FPI and HPCA. So electron number density up here and H plus number density. Another useful thing is to set the y-axis to log scale. So you just call options, give it the variable name, and the y log option, set it true. And then call tplot again, recreate the plots. And notice this time it's on a y logarithm scale. Let's see. So I guess we could go ahead and jump into the analysis tools now. We have a handful of analysis tools. There aren't a lot, and there are probably bugs with them. I don't know how much they're being used right now. So please, if you run into a crash or a bug or something you don't understand, please send us a bug report and let us know so we can get it fixed as soon as possible. So the first one is subtract average. This subtracts an average from the tplot variable. Just import it from pySPEDAS, and then call it on the tplot variable name. It creates a new tplot variable with the suffix, or dash D for the averaged. I think that's just so that's just like an IDL. And so we plotted the FGM data from before as well as the data with the average subtracted. And notice that it still has the vertical lines. That's because we attach those vertical lines to the tplot variable. So whenever you plot that tplot variable, it's going to have those lines. Another thing to note is that in IDL, if you call subtract average on a tplot variable, it'll actually carry the metadata with it. Right now, we're not doing that. And that's just a bug that needs to be fixed. So another example is subtract median. So just import subtract median and call it. And in this case, it's same variable name plus the suffix -m, just like an IDL. So you can plot the full FGM data, the average subtracted in the middle, and then the median subtracted on the bottom. And what if you want to time clip a variable, but outside of the load routine, say in a script? Well, you just import the time underscore clip from pySPEDAS, and you give it the variable names you want to do. You can give it a string, or you can give it an array of strings or a list of strings, and you give it the start time, the end time, and then a suffix. If you don't give it a suffix, it's going to append, I think, a suffix of dash time clip. If you do give it a suffix of nothing, just a blank string, it'll overwrite the current variables. So we went ahead and time clipped this down to, it was from, the time interval was from 6 to 7, but we just time clipped it down to 15 seconds, the last 15 seconds of that. So now we can plot that. It should just be those last 15 seconds. So yeah, and there we go. So this is the time clip data over here. And so what about clipping the data on the y-axis? So just like an IDL, we have tclip. So just import tclip from pySPEDAS. So from pySPEDAS, import tclip. And then call tclip. And again, this accepts a string or a list of strings, and then the bottom value that you want to clip, the top value that you want to clip, and a suffix. And again, we're given a blank suffix, so that it just overwrites the current variables. And just like it clipped them, and then we can call tplot. And so it should be clipped from 0 to 20. So now you can tell there's no more data below 0 and no more data above 20. And it's automatically interpolating between these two. So there is a routine TD flag that should be able to remove these the automatic interpolations, though I haven't actually tried that. So for future plans, I think a big thing is speeding up the CDF load times. Like in the past couple of days, we've really done a lot on that. And, definitely gone up like an order of magnitude in just the past couple of days. So we're making progress there. We also had a request for a searchable MMS events database. And I'm also going to do that in IDO. And we have to finish adding the corrected PEEPS omnidirectional spectra. There's a lot here for this. This is actually including the flat fielding corrections for the ions, the sunlight contamination, adjusting energy tables. The idea behind this is to get the same exact data product that we load in IDL in Python. Same with omnidirectional HBCA spectra. It's the data that's summed over the A nodes plus spin average. We want to provide the same tools for spin averaging and summing over the A nodes that we provide in IDL. We still have to add the spin average EIS and PEEP spectra, as well as the EIS and the PEEPS pitch angle distributions. Those are probably going to be pretty easy. Still have to figure out some way to actually display the FPI lossy disk compression and error bars. That way, when you load FPI data, you can actually quickly figure out which data are valid and which data aren't. Still need to add a read-only mirror support. This is so that you can load data from a local mirror so if you have the data stored in a local mirror, it would grab the data from the local mirror prior to trying to reach out to the SDC. And we still have a lot of tests to add, documentation and crib sheets, and definitely still need to add the center measurement keyword for FPI and HBCA. For those of you not familiar with this, I think most people are probably familiar with this, but by default, most load routines load the data at the center of the accumulation interval, but FPI and HBCA load the data at the beginning of this accumulation interval. And so in IDL, we have a center measurement keyword to make those consistent with the other load routines. And this hasn't actually been implemented in Python yet. So coming soon. So it's pretty much all I have.
Can I make a suggestion?
Yes.
So for example, in the plot that you're showing, the x-axis doesn't show the timestamps for short time intervals.
Yes, that's a great point. We'll definitely have to fix that. Cool. So I'm going to be releasing, actually, I've already released this it's under pySPEDAS, MMS examples, and the tutorials folder. And this whole script is available here.